Hello, I'm Paul Germain, your host for Smart Boating. As you know, if you watched the show before, we cover a wide variety of topics, from man overboard to insurance. And the general idea is to provide you with some information that will help you make smarter decisions and have more fun in the water. Today's show is right up that alley. We're going to be talking about weather with an expert in that area. His name is Bryce Williams, and he's out of the National Weather Service office in Norton, Boston area. Welcome, Bryce.
Hi, Paul. Thanks for having me.
Good to see you. And we've got a really interesting show here today. But before we get into it, can you tell people a little bit about your background in weather?
Sure. So I started out as a very young child interested in weather, as a lot of meteorologists do. And some of my earliest memories were hiding in the closet when we had a severe thunderstorm warning or a tornado warning in Texas. And that passion I pursued that passion in undergraduate school at Mississippi State, and I got my master's in atmospheric science at the University of Alabama in Huntsville, Alabama. So after that, I quickly joined the National Weather Service out in Spokane, Washington, and then recently moved here to Boston to join the Weather Service office here. So it's been a long journey.
Wow, that's great. Well, you've picked up a lot of experience working with weather, so you're just the right guy for the show today. So let's get right into it.
All right.
It's a big topic, weather. You can spend days, you can spend weeks, years, right? But we've only got a half hour, so we'll cover the highlights. And I thought what we could do is share with people basically how weather works. We've got a couple of graphics here that would help with that story, right?
Certainly. If we can go to the first graphic, I've definitely got one. So we kind of want to zoom out and see, how does weather start? What drives the weather?
Yes.
And the answer to that is pretty simple. It's the sun. As you see here, the sun's rays are what heat the surface of the earth. And so the lowest layer of the atmosphere is called the troposphere. That's where all the weather happens.
Right.
And so as the sun hits that, it heats the air up. Air likes to rise, and so air begins to rise and circulate.
Okay.
And it causes what's known as these global circulations. And on this next graphic here, you can see how that kind of works.
Okay, and we know that, that it's going to work differently at the equator than it is at the two other ends of the globe, right?
Exactly. So like you see here, at the equator, we're going to have more insulation, we call it, so more heat reaching the surface versus the poles. So up at the poles, you get less because the sun's rays aren't coming in as perpendicular as they are at the equator.
Right.
And because of that, we get differential heating, or heating of the surface differently across the globe.
Okay.
In addition, water heats up less quickly than the land.
Right.
So all this together means that we kind of have all these undulations rotating of columns of air, and you see here, at the equator that it rises and it moves up to the subtropics and sinks and causes these areas of what are known as high pressure and low pressure.
Okay.
May have heard of highs and lows. We've seen them on a weather map.
Yes, yes.
And so these, we have these all across the globe, and the atmosphere is always trying to bring itself back to balance.
Really? Okay.
So you can see how this map here shows we have
This is a snapshot,
this
right?
is a snapshot of one moment in time. So
Yes,
it's not
right.
always going to look like this.
Right.
We have high, for instance, on this map, you see a big low pressure system over the Texas or the Southwest.
Yes.
High pressure over the Atlantic. That's just one snapshot. We kind of have an idea that low pressure means stormy weather. High pressure typically means good weather.
Okay.
So if you just want to get a good snapshot, you're heading out, look at the highs and lows. And if you're
Okay.
near high pressure, you're typically going to be in better shape.
Oh, that's good to know. So look for the high pressure.
Yep.
Okay. Well, I get this next graphic because a lot of people say, that sounds pretty simple, pretty straightforward.
Sounds like it.
Get the heating, the air rises, it moves around. Doing a forecast must be like shooting a fish in a barrel, right? Well, what's the scoop here? Like even this graphic we have up here shows that you go out 3 days, you get quite a margin of error possible, right?
Yes, I wish it was that simple, but unfortunately it's not. It's a very complicated process, simply because there's so many things that go into making the forecast. So imagine it like a recipe. There's so many ingredients, and if one of those ingredients is off by even a little bit, it can throw off the whole thing, the whole end product.
Yes.
So for instance, here you can see this graph is kind of showing the amount of error in storm location that we can get even 3 days out. So if we're tracking a nor'easter, say, 3 days ahead of time, we may be 200, 300 miles off of exactly where that storm center is going to be.
I see.
And the biggest reason for this is typically problems with our observations of what's happening right now. Basically,
Okay.
what meteorologists call initial conditions. And so if these are wrong, and those wrong observations go into the equations that we use, that's going to throw everything off. And that problem gets bigger and is exacerbated with time. So the farther out in the forecast we go, the bigger those errors are going to get. And you can kind of see that on this next graphic.
Yeah, it doesn't have to be very much, right? You could be 5 degrees off on the initial measurement of the temperature, and it has big ramifications with the overall picture, right?
Exactly. Say we think it's 85 in Boston when it's actually 90, and put that into our calculations, and that's going to throw a lot of things off, not just the temperature forecast, but the storms and rain and thunderstorms and such too.
Yeah. So it's a multivariate equation, which results in different line patterns like these, right?
Exactly. You may be familiar with what are known as spaghetti plots. This is what this is called, and we see these during the tropical season, during the hurricane season. This is an example showing a hurricane track forecast, and you can see in the bottom right here where the line starts, the lines are much closer together. There's much less spread because we're earlier in time. The farther we go out in time, 2, 3, 4 days, the more differences there are in each perturbation of the forecast. So you see that they spread out and they get farther, and we get less certain of exactly what's going to happen.
Right. So occasionally you'll get a big miss like this picture here. Right?
Yes. So this is kind of one of the infamous example of a time when our forecast models kind of didn't really have a grasp on it because of a lot of different factors, but one of the things was not enough data, not enough good data to bring into those models. This is known as Hurricane Sandy or Superstorm Sandy, as many people may remember it, and it came up the East Coast, and you can see it here to the east of Florida. And as it made it its way up the East Coast, our models were thinking initially it was going to turn out to sea, and of course everyone knows that it eventually hooked left back into New York City and caused a bunch of damage and destruction. So it's definitely not a science that's totally finished. We're always learning, and it's something that we're always advancing in.
Well, you know, there's some primary families, if you will, of clouds that can help somebody understand what's going on. So someone's heading out, particularly in a smaller boat, 19-foot Mako, 16-foot wheel, or whatever. They may have electronics, not have them on. They may not have an electronics. But there's a lot of things they can observe through the clouds and the wind direction that will help them out. And this is kind of an interesting shot because it's, you know, the old expression, sailors take red sky at night, the sailors take warn, or something to that effect.
So there's a lot you can get from just a visual observation of your surroundings. And so that everybody's kind of familiar with that saying, and it actually has a lot of merit. So it's a red skies at night, sailors delight.
Right.
Red skies in the morning, sailors take warning. And there's a meteorological basis for that. Because we know up here in the mid-latitudes, our weather systems typically move from west to east. And so at night, when the sun is setting in the west, it rises in the east, sets in the west. So when it's setting in the west, that means that it's illuminating clouds to the east. That's beyond to your east, so the storm's leaving. That's why that would be happy. You know, the storm is gone. In the morning, red skies in the morning, the sun is rising in the east, illuminating clouds to the west. So it's coming. The storm's coming towards you. That's why it would be red in the morning. And so that's just kind of an old saying that people
reliable,
hear. But it's very reliable. It really is, and it's based on things based in meteorology.
Let's talk. We've got these 4 major categories. This one is the highest level clouds?
Yes. So I wanted to talk a little bit about what kind of clouds can tell you maybe what's coming. So this is an example of, we're going to start at the highest levels of the atmosphere. These are cirrus clouds. They are noted because of their wispy nature visually, and that's because they are so high up that they're so cold that it's made of ice crystals, the cloud, instead of droplets of water. And so, you know, typically these can be a fair weather day cloud, but what we're looking for is the progression of this to the cloud that we're going to talk about next. And these are called stratocumulus. Cirrostratus. Cirrostratus. And so what happens is we're looking for a progression from cirrus to cirrostratus. This is basically a thickening and lowering of the clouds. So if you're starting to see the cirrus get thicker to where you're not able to see any more blue sky, and they're starting to seem lower and they're starting to lower down, that is an indication that what's known as a warm front is moving through, or is about to move through, and that is a harbinger of unsettled weather of stormy weather to come. And we'll talk a little bit about that later, but cirrus to cirrostratus is something that typically means weather's on the way.
Okay, that's something you can observe and anticipate what's cooking.
Exactly. Now that's on the, we're talking a time scale of hours ahead of time with those. With this next cloud, the towering cumulus clouds, we're talking severe weather or stormy weather is imminent in the next half hour or less, depending on how close you are.
Yeah.
So we're looking for these tall, vertically stacked clouds, very puffy typically, and that's because of these thunderstorms have these updrafts. That's basically the rising air in the middle. That's the lifeblood of the storm.
Yes. Makes
them very tall, and that's what makes them notable as thunderstorms. And so if you see these on the horizon, you know that you should be trying to go into harbor or avoid them as best you can.
That's bad news right there, right?
Yes.
And how about this one? This is kind of a lot of information on this slide. But if we start in the top right-hand corner there,
sure,
shelf cloud.
Sure. So this next cloud is called a shelf cloud, and it is associated with a thunderstorm. And what happens is, if you look in the top right-hand corner, how this works is we have the updraft that I talked about. The red arrows on this graphic are showing the warm rising air feeding the thunderstorm, while the blue arrows are showing cold air and rain that is falling through the storm. And what this does is this hits the ground and then spreads out very quickly as what's known as a gust front. Basically a really windy, 10 to 15 minutes that you're going to experience.
Yes.
And so on the front of this gust front is what's known as a shelf cloud. And you can see examples of these on the left here. These two leftmost images are what you might see if a shelf cloud is approaching. And what that's going to tell you is that you need to batten down the hatches and get ready for some strong winds, because shelf clouds mean strong winds are incoming. Now, if you're looking at a radar, which we're going to talk about here in a minute, this image on the bottom right is what you would see, kind of a linear line of storms headed towards you. You know that strong winds are on the way.
Yeah, okay. Now, speaking of wind, that's another thing you can be aware of. And in the right-hand portion of this graphic, it shows how winds can come together, fronts can come together.
Exactly. So even if you, again, don't have too much equipment, just from observing the wind direction and especially changes in the wind direction, can tell you a lot about what to expect in the next hour or so. So we know, see on the graphic on the right here, we have the L. The big L is our low pressure system, our storm system. And behind the warm front, which is the red line, we have the southerly warm air. So if you're experiencing warm air out of the south, you're probably behind a warm front, and what that means is a cold front is probably approaching soon. And what cold fronts do is, when we have the cold air bringing in and clashing with the warm air, that's when we get stormy weather. So you know that if you have southerly warm flow, a cold front and thunderstorms are probably on the way. When that wind turns to the west or the northwest, that means the cold fronts come through, and you're going to eventually get some drying air behind those storms.
Yeah. Okay. All right.
So now if you look at a snapshot on the left here, this is a typical map of the United States, and you can kind of look and see where you are in relation to these warm fronts and cold fronts.
Right. That's good information. Now, Bryce, what I find myself in a situation commonly is that I'll listen to the forecast on my marine radio, and I'll be in a slightly different spot than what's forecast. Say, I'm in Manchester, I'm going to Gloucester. There's a forecast for Salem, which is a couple miles away. And oftentimes I have trouble connecting that forecast information with what's going to happen to me. Certainly the marine radio is a good start to be aware, but what's another approach there? Should I be maybe employing a radar application or something?
Sure. So you always want to be situationally aware of where you are in relation to certain locations on the land, because when you're using this, like you said, this marine radio is a very useful tool for having a heads up. But it's not the only thing we have. Luckily nowadays, with technology the way that it is, we have phone apps, and if we have internet on our phone when we're on the water, we can pull up a radar. And so this is an example of our radar, radar.weather.gov. You can go to our website, or there's a lot of apps out there that have radar. Basically, you can see where you are in relation to a storm. So not only just having to interpret it from the words on the radio, you can visually see, okay, I am directly east of this storm. It's moving towards me. I need to get out of the way or get into harbor quickly. So the radar is a very useful tool.
So a smartphone can be very, very helpful.
Smartphone is very helpful in these situations.
Yeah, good. Thunderstorms. Boaters, including myself, worry about them constantly. It appears from this graphic that there's three underlying components to it, and we're going to dive a little deeper on each of those, right?
Exactly. So we typically worry about thunderstorms, especially in the summer months. That's because we have all of these ingredients. So we're going to start with the first ingredient, with the most important, which is moisture.
Okay.
So every thunderstorm needs moisture. So we fortunately or unfortunately, however you want to look at it, have lots of sources of moisture. We're surrounded by water. So we have the Atlantic Ocean. We also get moisture even from the Gulf of Mexico and sometimes from the Great Lakes. In some instances, it's a lesser extent, but we have moisture available pretty much all around us. So that's never really an issue.
Right. So that's component number one.
Exactly. The next component, the next ingredient that we need is known as instability. And so as meteorologists, we know a general rule that warm air likes to rise. So when we have an atmosphere where you see this graphic here shows the bottom layer of air is warmer than the layer above it.
Yeah.
So that's going to mean that it wants to rise. It wants to start lifting.
Right.
That's instability.
Right.
And that's when we get those towering cumulus clouds that we saw on the graphic earlier. Now those are two ingredients. We still need a third.
Yes.
And that is a source of lift, something to kick it off and get it going.
Yep.
And two of the most common that we see here in southern New England are fronts, warm fronts and cold fronts. So with this graphic here on the right, the image on the right, you see a warm front. And that's what we talked about earlier with the southerly winds.
Yes.
The warm front comes through and causes those clouds, the cirrus, to turn into cirrostratus and eventually lower down and cause rain.
Okay.
And then eventually the cold front on the left here comes through and turns wind out of the west or the northwest, and it kind of acts like a bulldozer, pushing that warm air ahead of it and making it lift. That's why we get thunderstorms associated with cold fronts.
Wow. Okay. Now here's a quick snapshot of the different stages.
Yes.
It's an initial stage, a kind of a dangerous stage, and then a dissipating stage.
Exactly. There's three stages of every thunderstorm. We start with the cumulus stage, basically just a puffy cloud. And in the middle image here is the mature stage. That's where the thunderstorm is most potent and most dangerous. You have the red lines meaning the warm air rising and the blue lines indicating the cold air falling, and that's when it's at its peak until eventually that cold air cuts off the warm updraft and it dies in the dissipation stage.
Right. And of course, that's not the only component that's dangerous in a thunderstorm. Lightning is super dangerous, right?
Lightning is very dangerous. Yeah. It's actually the #2 weather killer across the country and even across the world. And especially as boaters out there, we're oftentimes the highest, the tallest thing out there. So we definitely don't want to be out there during a thunderstorm. And one thing that's concerning and most people don't know is lightning can actually strike up to 10 miles away from a storm. So you don't even have to be able to see the storm to get struck by lightning. We like to say when thunder roars, go indoors, because that just means if you're close enough to hear the thunder, you're close enough to be struck by lightning, even 10 miles away.
Right, and there's an example of what happens if you do get struck.
Exactly.
Right?
Not a good outcome, nothing that we want to experience. This is not good.
Bad news.
Exactly.
Talk briefly about hurricanes. The top right-hand part of this graphic shows a satellite view. And then can you fill out the rest of the picture for us, just real briefly?
Sure. So hurricanes are basically just tropical storms that have very strong winds, 74 miles per hour or more. You see some examples here. The top right is the view from space from our satellite. You can see the eye there. The bottom right image is our radar view, so basically seeing the rain bands rotating around the center, moving in to the coast. And then this left image is another satellite view, but it's actually showing the temperatures of the cloud tops. The color scale is kind of reverse of what you would think. Those reds mean very cold cloud tops, so very strong storms within the hurricane.
Bad news, right? Now we know they have 3 ingredients, right?
Yes, so they have specific ingredients that they need to form, and those ingredients are often available in the tropics, which is why we get those storms forming in the Caribbean and off the coast of Africa. They need the really warm water, 80 degrees Fahrenheit or more. They need the deep tropical moisture, so lots of moisture, and then they need the winds to be light, not turning too much with height.
Right, so people see this a lot on TV, you know, the different thunderstorms, and they're probably familiar with the 3 phases, but it's important to understand that there are 3 phases.
Yes.
And I guess you can get a ripple effect. You can get the outcome or the impact of a storm prior to it arriving, right?
Exactly. So we do have a progression, so that the storm's not just going to pop up and surprise us. We have a progression from a tropical depression, which is the wind speeds, the least wind speeds, then it moves to a tropical storm as it increases to 39 miles per hour or more, and then eventually a hurricane at 74 miles per hour. Now, like you said, we don't have to be experiencing the hurricane right here to experience effects from it, like the choppy surf, the bigger waves. We can get those out ahead of the storm 2-3 days in advance, depending on the track of the storm. So you've got to look at the track. If it's headed towards New England, even if it's hundreds of miles away, it can be sending big surf ahead of it.
Yes.
Whereas if it's headed, perpendicular to us, then we're pretty safe from any choppy swells ahead of it.
Okay, all right. Here's another. We're going to be running short on time, unfortunately, shortly here. But I wanted to cover fog because fog is a big issue for people. We got some pictures of fog here, but can you explain a little bit about fog, where it comes from, and how it works?
Sure. So in southern New England, oftentimes our foggiest times are in the mornings and in the springtime, because the way that this fog works is you have the warm, moist air flowing over the cold water, and so that brings the air down to its dew point. When the temperature and dew point meet, it forms fog, and so that's why we have such so much fog in the spring and at nighttime, because it cools down and the air becomes more saturated that way.
I see. Okay. All right. Now, this is a common situation, particularly down east, as they say, up in Maine. They have the perfect conditions for fog. So if you're unfortunate enough to be caught in this fog, as you say, that comes in at certain times of day and so on and so forth, are there tools that you can use to become aware of it?
Certainly. So on our website, I think I have a graphic showing if you have internet access, this is where you can find a satellite view of fog from our website. So there's a link here, and what this next slide shows is an example of even at night, we can see fog oftentimes on satellite. So this is showing some low clouds and some fog, but depending on it doesn't work every time, but depending on the situation, you can oftentimes see how much fog is surrounding you. If you're close to the edge of the bank, maybe you can start heading that way, try to get out of it, or if you're going to have to just wait around for it to dissipate.
Right. How is there any way of judging how long it would take to dissipate during the fog?
There's no real rule of thumb because every situation is different. But generally, in the morning as we get towards the mid-morning, that's when it's going to start dissipating. So if it's still 2-3 a.m., you've probably got a while. But as the sun rises and it starts to mix the atmosphere, that's when it starts to dissipate. So the closer to the sunrise or past the sunrise you are, the better chance you're going to be able to get out of it here soon.
Okay, all right. Well, that's good to know, particularly if you're stuck in the fog.
Exactly, not somewhere you want to be.
Now, your National Weather Service, NOAA, has a number of different applications available through the website, right? And we've got just a few here to share with people. This one is an overview of the Weather Service, Marine Weather Service, right?
Yes, so basically something that you want to check every time before you go out. You want to check the marine zone forecast. So you can see here under forecast in the marine. This is our website, weather.gov/Boston. And you're going to click this link and it's going to bring up a forecast for that whatever zone that you click on the map. So wherever you're headed with your boat, and it'll tell you what the winds, the waves, if we're expecting fog. So that's really the best way to not get caught, is to check the forecast before you go.
Right, okay, all right, because it's pretty good, you say, forecast or forward-looking picture of what's going on, so that you avoid the surprises that way.
Exactly.
Yeah. How about this one here, graphical?
Yeah, so this is another way to look at the forecast. If you want to see, if you're planning out a trip and you want to see what the waves are going to do in a certain area or at a certain time, and you want to visually see it,
yes,
you can go to this website, digital.weather.gov. It'll plot all of everything: wind gust, wave heights, visibility, so fog, forecast, everything on a map. So if you don't want to kind of see it in text, you can see it visually here.
That's nice. That's nice.
Very helpful.
Again, the idea is to get the forecast before heading out.
Exactly, beforehand.
I think we've got one more here.
All right, and then the last one I wanted to show is these observations that we have from buoys across all of our outer waters and some of our inner waters, and they can see you can see things like wave heights, visibilities, wind speeds, all sorts of information that could help you decide whether or not you want to head out or when and where it would be safest to head in. So again, at weather.gov/Boston, you can find all of this information.
Right, so I could get it on my tablet, I could get it on my smartphone,
exactly,
get it on my home computer.
Mobile friendly, so you can get it from any of those devices that you choose.
Right, and in general, my understanding is this is the foundation for information that are shared by other weather forecast services. This is the basic data.
It is.
This coming from these.
The Weather Service provides the foundation of all of these forecasts that you see.
Why not go to the source, right?
Exactly.
Yeah. Well, that's we've covered a lot of ground here on weather.
A lot of stuff.
Just to recap, we've talked a little bit how the weather basically works.
Yep.
With the heating and then the air rising and the currents and the rebalancing.
Mm-hmm.
We've talked a little bit about the different cloud formations, the four basic groups, right?
Yep.
And we've talked about observational things that you can do observationally, some of the tools you can use. So it's a lot of ways that boaters can keep safe and have a good time out there. Anything else you'd like to add before we wrap up the show today?
That you pretty much covered it, Paul. I want to thank you for having me. I just want to reiterate, that boaters can be proactive in checking things before they head out. Check weather.gov/Boston or weather.gov for any of our locations across the country that you're heading out. There's all sorts of tools and technology that is available to us now on our phones and our computers that can help people stay aware and stay safe when they're out in the water. So weather.gov is a great resource for everybody.
Right. Well, thank you for joining me today.
Thank you for having me.
And thank you, Smart Boating viewers, for joining us. If you have comments, questions, or just want to watch another show, join us at www.smartboatingus.com. Thank you.